And now, geez, almost every week, somebody's sending me a paper about some new, experiments done, and scientists saying this and that about it's a virtual reality. And about a year ago, there was a group of physicists, very top-end, high-profile physicists. It was a couple from CERN in Europe, and there was MIT and Caltech, and all the big names in science and physics. Anyway, and they were all represented on this panel, and the panel was called virtual reality. So here was all of these, top-end, very best institution physicists all sitting around, all of them convinced that reality was indeed a virtual reality, that reality is information, and they didn't really know what to do with it at that point. It's like they'd gotten that far because that's what the experiments told them, but they just didn't know how to go forward with that. So they were having this discussion about virtual reality, and it was under some sort of a larger science forum where they had various discussions in various areas. But here it is now, a little more than a decade later, and we have major institutions all sitting around a table discussing that surely this is a virtual reality. That's where all the experiments are pointing us. And, what does this mean? And where do we go from here? So now you have the player and the consciousness have to be non-physical to the virtual reality, as seen from inside the virtual reality. And what's going on is the player's making choices for the avatar, the elf, and the computer's computing the consequences of those choices in a multiplayer game. So now if we look at us, then okay, the physical body is the avatar, consciousness is the player, and another part of that consciousness system is the computer. Because both of those have to be, consciousness. If you're in that same reality frame as consciousness, then you're consciousness too. So consciousness is the computer, consciousness is the player, you see, and that's just the logic of a virtual reality. A virtual reality can't be any different than that. If it's a computed reality, it's got to be computed someplace. It can't be computed inside the virtual reality. It's got to be outside. And if it's outside, it's non-physical from the viewpoint of being in the virtual reality. Mm-hmm. And it shows, we're finally getting out of the box. People are seeing bigger pictures. I think they will find that the holographic metaphor will kind of run dry after a bit and not really work so much for them, as the fractal will be a better thing. And that this is a fractal reality is kind of staring us in the face, because how do you make videos these days that with mountains and trees and skies and water and clouds? Well, they're all created by fractals.
Yes.
So the fact that this reality is a fractal reality, and it's a computed reality, and you can make shapes and and things that look just like this physical reality by computing with fractals. Mm-hmm. So that's kind of a hint that really the reality is one computed, and to that, reality is basically a fractal process. And
the first thing that jumps into your mind, you go, how does this work?
Yeah.
So basically what it means is, in our terms, and I have to emphasize that, in our terms, the universe literally blinks on and then collapses to a single point. And you have to think about that for a minute. So just before the universe collapses to this single point, how much distance is there between galaxies? 0. There is no distance. Distance itself is an illusion. Time is an illusion, and distance is an illusion. In fact, the two things are related by mathematical equations. And if time is an illusion, then distance is also necessarily an illusion, and that can be expressed mathematically. So if we time it just right during this, and I can explain it or describe it as a sine wave, the universe blinks on and off like a sine wave. So above the x-axis, for the engineers out there, above the x-axis we have a positive part of the sine wave, and below the x-axis it's a negative part. And we can call the part above that x-axis matter and the part below the x-axis antimatter. So we have a cycle of matter and antimatter in a blinking universe that blinks at 1.039 trillion cycles per second. And it's possible to calculate this. You can actually calculate it several different ways, and this is very important. There isn't a single calculation. There's 3 different mathematical approaches that all give you the same answer. Okay? Mm-hmm. The first one is helps you understand the relationship between the various frequencies that are being used. The base frequency is called electron spin resonance, and that occurs at a frequency of 1,015 megahertz. Okay? Mm-hmm. And if you multiply that times 1,024, you get 1.039 terahertz, or trillion cycles per second. And it's very important, this number 1,024, where does that come from? That comes from the actual number of elementary particles that exist in our universe. And I know I'm going to get some pushback on that, because there's going to be some physics folks out there going, there's only been 17 elementary particles demonstrated. And he would be correct. The mathematics to demonstrate that we actually have 1,024 elementary particles is part of a very simple math pattern that's called quadrature amplitude modulation, QAM. And this is a mathematical pattern that's used for a Wi-Fi signal. It's the exact same math that's used for a Wi-Fi signal or a cable TV broadcast.
Now, there's a problem with this, which some of you, I'm sure, are thinking, I hope anyway, which is what's called the grandfather paradox, which is the old conundrum that haunts all time travel schemes, which is, if time travel were possible, you could go back in time and kill your own grandfather. Well, then you wouldn't exist. Well, so then this sets up a logical impossibility. Either you exist or you don't exist. And some science fiction authors have assumed that somehow massive influxes of synchronicity would preserve your grandfather. You know, you would approach him with your Saturday night special, but it would blow up in your hand, or it would ricochet off the St. Christopher medal he always wore, or something like that, because he cannot be killed by you, because in that case you wouldn't exist, in which case he couldn't be killed by you. And this troubled me for a long time then. What exactly would happen in this situation if a time, because the according to Hans Moravec of the Robotics Institute of Carnegie Mellon University, I mean, time travel is no big deal. The first paragraph of this paper, the last few years have been good for time machines. Kip Thorne's renowned general relativity group at Caltech invented a new quantum gravitational approach to building a time gate, and an international collaboration gave a convincing rebuttal of the grandfather paradox arguments. Another respected group suggested time machines that exploit quantum mechanical time uncertainty. The technical requirements for these suggestions exceed our present capabilities, but each new approach seems less onerous than the last. There is hope yet that time travel will eventually become possible, even cheap.
Are there fields of awareness in the fabric of space itself? Is there consciousness beyond the physical? Is this the secret to enlightenment? And can scientists verify that the field of awareness actually exists and pre-existed the Big Bang?
level is that helium cannot be frozen solid. You can freeze hydrogen solid, you freeze carbon dioxide solid, but helium, for helium to become its atoms to align in a solid form would violate the uncertainty principle, and nature doesn't seem to allow that. So you can't, no matter how cold helium gets, it remains a liquid. That, to me, if you can have a beaker full of liquid helium, and that exists at our level of existence, and it's a sort of manifestation of the uncertainty principle, and it's where it's sort of slipped over into our world. There are other things going on right now where there's a device called a squid, which is a sort of electrical coil, in which it looks like we may be able to demonstrate that the current, if you say which direction is the current going in the coil, it's going both directions at once, which is kind of an impossibility, but to simultaneously do that, that too is a quantum phenomenon, that these two realities are overlapping. So I think we will cross that barrier.
Well,
Well, this gets away from Bowman into Pribram, but it's equally interesting with equally profound implications. Pribram, as I said, says that we're thinking with holograms inside our head, and that out there exists something that's more akin to the radio waves in the room from which your TV gets the image. So in essence, we're kind of conscious TV sets. And what we think is reality when we look out here is really just the image on the TV set inside our mind, but doesn't exist out there. And Pribram says this is why there's all kinds of evidence that we seem to respond more to the models of reality in our head than out there. In that pool of our brain, they're sending out ripples that are constantly crisscrossing. And he believes that's what the brain hologram, that's how we think and how we remember is through that hologram inside the head.
it would apply in another sense, too, because if you take a hologram image and cut it in half or in quarters or in tenths, each time you reduce it in size, the image becomes fuzzier and fuzzier, even though the whole image is there, just the way memory would seem to be. And
it becomes fuzzier when you have portions of the brain removed.
Yeah.
Correct. Other investigators. And that is another very interesting thing. As you know, Mother Nature uses all kinds of mathematical languages. That when we go to understand physical phenomena, we generally find that there's some sort of mathematical underpinning to whatever the phenomena is. There are uncountable mathematical languages. It turns out that the mathematical language involved in the making of a hologram is a system of mathematics developed by a Frenchman named Fourier. They're called Fourier transforms. Well, it also turns out that our brain uses Fourier transforms to translate visual information. And this is a very unusual state of affairs. It's kind of like discovering Eskimos speaking Spanish.
Mm-hmm.
You know, it's not proof that the brain is a hologram.
Mystic worldview. So what you're saying is that science has shown us something that scientists do not want to see.
Well, they become so used to the way of seeing it that they don't want to change it. You see, they feel uncomfortable about changing it, and they feel there's no reason to change it. Many of them, they say, well, we're doing so well now, why should we change it? The evidence in physics comes partly from relativity and partly from quantum theory, or perhaps more from quantum theory than relativity.
And what kind of evidence is that?
Well, in relativity, we have a notion of a universal field, which is dynamic, flowing, and according to Einstein, particles should eventually emerge out of this as singularities or very strong regions, stable pulses of field, which gradually merge, the fields gradually merge with other particles. So we have an unbroken universe, which is in constant flow dynamically. And even the very notions of space and time have become relative, so which were previously absolute. And they may even go on to singularities like the black hole or the supposed beginning of the universe, where the present laws would break down altogether, all concepts that we know. So that's a very revolutionary view compared with what we had, say, a century ago. And then there's quantum theory, which perhaps is more revolutionary. And it's hard to explain that in a short time, but there are three main features, I'd say. One is the notion that a quantum process is in some sense indivisible, that it is one whole which it can be broken, but then it becomes an entirely different process, so each process is a whole. Otherwise it can't be what it is. And all the quantum processes of movement are linked, as it were, into one whole. Now, the second point is the wave-particle duality, the discovery that, say, electrons, which are normally and classically particles, can behave statistically like waves in a more precise experiment, and light, which is classically a wave, can behave like a particle in a more precise experiment. So it seems we have these two aspects which depend on how the system is treated, context dependent, which is quite different from the classical idea that whether it's a wave or a particle is intrinsic. Now, the third point is what's called non-locality, that we find that in certain conditions there's apparently an immediate connection of distant particles. It's rather hard to explain. We can't use it for signals, but still it seems to be there. It's connected with the experiment of Einstein, Podolsky, Rosen, and has been checked by, they've been tested by Bell's theorem and Aspect's experiment. It seems pretty well established, both theoretically and experimentally. Now, again, all of these you see combined to the notion that the universe is a kind of indivisible whole, rather than analyzed into constituent elements which interact as separately existent.
So this unity also creates a kind of ordering of things.
Yes, it can create a kind of ordering of things, but at the same time it explains, you can see that there are situations where we have this high degree of order and others where we don't. That it's possible within the mathematics to see that when something called a wave function can be represented as a product of independent factors, and all the particles behave independently. But in a more general situation, they don't. So you can explain why we have so much independence in ordinary experience, and yet why, in a more careful probing, we find order, new kinds of order. See that I say that I'm going to introduce an entirely non-classical concept, which is the activity of information. You see that it contributes fundamentally to the properties of substance. Now, the fact that you still think of a particle doesn't say that it's classical, you see.
But in some senses, your view is more classical than the Bohr view.
It's more like the classical, yes. I wouldn't call it classical. It looks more like the classical, but it's also quite different.
So could you say that it's the classical worldview, but with information?
Well, some other things added as well, but which I haven't gone into. But I think that when you have changed the concept so much, it wouldn't be right to call it classical, you see. I think the main point, it's hard to say, the main point about would be rather whether we want to take the wave function as the whole description or not. See, I add this particle, right, and say the wave function has the meaning of information that acts on the particle. Right? Now,
maybe you should explain the wave function.
Yes, this wave function is a mathematical representation of the field of information, you see. In the case of one particle, it's like a wave, but it's a wave that acts according to its form and not according to its intensity. With many particles, it's more complex, you see.
And in the Bohr interpretation of atomic physics, you would say that the wave function is just something that we make up to describe.
We make it, well, it's something that Bohr called it an algorithm for calculating experimental results, right, in the phenomena. The wave function is part of an algorithm. You know what an algorithm is,
A way of calculating.
A way of calculating, yeah.
And no more than that.
No more than that. Now, von Neumann said something a little bit different, that the wave function is a complete description of the quantum reality. Now, it's not clear whether Bohr would have ever talked of a quantum reality, because he only talked of this whole phenomenon.
But then in your interpretation, it's very important that the wave function is not just part of our description, but part of...
We regard it as part of the reality. And see, this would be, if we make an analogy to society, one view would be, say, society consists of a lot of people that you could see interrelated. But another view is to say they're interrelated by information exchange, right? Saying that's crucial. Without that, the society would collapse, right? Would not. So I say that's part of the reality of the society, right?
And could you elaborate on your view if you take it to societal analogies? How is your worldview if you give it as a description of human affairs and society?
Yes, well, see, if we think of society, you see, if you compare, you can have every individual trying to follow his own pool of information and leading to chaos. Or you can have people trying to move together with a common pool. And of course, you can have the attempt to impose a pool, but you see, but that might lead to a conflict with the pools that are already there. See, I think it's essential to have coherence and order and harmony, that the whole society moves together with a common pool of information, like this ballet dance, which is not imposed, right? But which is established by exchange and dialogue, right? But, you know, the general trend hasn't got very far, you see, because everything is divided into nations and religions and other kinds of groups which behave as if they were independent, you see, and when they're not. So people will have to give all that up, and they may find it hard, you see. To deal with the ecological problem, I think people will have to give a great deal of that up.
So you're moving your emphasis from the persons, the individuals, the divided parts, to the information flow or the information field of society.
Yes, that's right. But I say each individual contains the whole information field of society in his own way. So, well, it's in his mind, in his brain. You see, everything you know comes from society practically, right? It may be both information and misinformation, right? But it determines what you do, right?
But you have to read books to get the information.
Yes, but that comes from society, right? Books are part of society. They wouldn't exist. So I say that the individual is formed out of society, but together the individuals form society, right? Now, well, you see, it's a question of whether you have a holistic approach, which puts the whole as primary. See, in classical physics, the parts are the primary concept, and the whole is only an auxiliary concept, which is convenient for when you have many parts working together like a machine. But the parts are taken as the basic reality, right? And saying just subjectively, we find it convenient to think about the whole. But in quantum mechanics, I think there's something else, that the whole is objective, and the parts are the result of analysis. But we have large areas where the whole behaves to some extent like independent parts.
All I know is this is the kind of stock Mr. Drysdale thinks is good.
What does that say?
IBM.
What's that spell?
IBM.
Reckon I ought to do it.
Operator.
Oh, howdy, ma'am. This here is Jed Clampett. I'd like to buy some stock.
What number do you wish?
Number? Oh, a couple of goats, 3 pigs, 4 cows, a bull, a mule, and a dozen chickens.